الو 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 السلام عليكم. الو حد سامعني؟ سامع؟ ايوه هسه سمعت. ايوه اوكي. لانه فيش الا بس انت وفي معتصم ياسين، بس مش شايفه. اوكي على كل الاحوال نكمل الشرح. هذا الكلام شرحناه، وهذا شرحناه الزاوية برضو كمان. في اي سؤال؟ لانه هو الفيديوهات مشروحة، يعني احنا مطلوب منا على فكرة يعني الواحد يعمل فيديو ويعمل له يحطه على الاي ليرنينج، واذا في سؤال احنا مستعدين. يعني هناك الشرح وافي، شرح وكنت بكتب اثناء الشرح، فهون عشان الاسئله بشكل عام. يعني في اي سؤال؟ هي بس تعرض انا هذا الرسم طبعا شفناها في الصف، هذا مرسوم وهي البرنامج الكمبيوتر برضه موجود. هذه وصلنا هون احنا، اذا بتتذكر اخر شيء وصلنا عند هون، مش هيك؟ اه فهذه سهله كانت، اللي هو الكي فيرتيكال اللي هو 2 باي اوفر لامدا فيرتيكال equal the component of k in the vertical direction, which is k naught times sin psi. So k naught sin psi, and k naught is 2 pi over lambda naught, and you will obtain lambda v equal lambda naught over sin psi. And if we want, we use these two equations here. And if we want, or if the surface of the earth is to be considered as smooth, then the maximum variation here in the vertical direction should not exceed lambda vertical over 10. And this is, and if you want to calculate the phase difference also, this equation gives the phase difference due to this movement from here, vertical difference from here to here, then it is k naught sin psi, which is k vertical, okay, twice, because distance is twice z, we go down z and we go up z, and this you will get the angle in degrees or radians. Here in radians, because if you put 2 pi, it will be in there, and then you can convert it to degrees. Okay, this is an example. The frequency is 100 megahertz, so the wavelength is 3 meters, lambda equal c over f. The angle is 2 degrees. The angle is like this. This is the earth surface, for example, like this. Okay, and this is 2 degrees, means that the angle is like this. By this, this is the angle here. This is psi. Very, very small, 2 degrees. This angle here. Are you with me?
Yes.
Okay. This is the 2 degrees. This is the angle. This is psi. Yeah, this is very small angle. Now, as we said, lambda vertical over 10 is the maximum height of the vertical variation in the earth, which is equal lambda naught over 10, because this is lambda naught over sin psi is also delta z maximum over 10, because this is lambda v over 10. Lambda naught over sin psi is lambda v and over 10 here. So lambda naught is 3 meters and 10 is as it is, and sin psi we put psi because psi is very small. So we convert it to rad, it will be 2 over 60 rather than 1 over 30. So here it will be 3 over 10, here 3 over 10, here 3 over 10. And the angle is 2 over 60, here 2 over 60. And we get 9 meters. So this means that at 100 megahertz, if the variation in the surface of the earth is up to 9 meters, it is considered the earth is the wave sees the earth as if it is smooth. If the variation is greater than 9 meters, the wave sees the rough earth surface if the vertical variation here, delta Z, is less than 9 meters, the wave sees a smooth earth. That's all this story. That's the whole story. Now this, as you know from physics, that when you have N2 refraction index is less than N1, the wave deflects to the right here. The angle will increase, the angle of incidence theta 1, theta 2 is greater than theta 1. And as we know in the atmosphere, when we go up, okay, the density will decrease as we go up. So N2 is less than N3, less than N2, less than N1. So N1 is greater, as you can see here. So if you divide the atmosphere into small layers, you can see that the wave will not move in a straight line. It will move in curved line, like this. Okay, that's the explanation here. And the refraction index is defined as square root of epsilon r of the medium. And to use straight rays, we use an effective earth radius of 8,497. I have explained that in the video. How do you obtain this? And this is also r squared. This is Pythagoras law, as you can see. This effective earth radius. So this length squared is equal to this squared plus this squared. So this is squared, r squared, is equal this squared minus this squared. So this is h1 plus ae all squared minus ae squared. And you simplify, you obtain this value. And since h1, the height of the antenna, is much less than the radius of the earth, we can cancel h1 squared. And r squared is equal to twice aeh. And r is square root of this. And this is called dt. This r is called dt. This dt here. The maximum distance. Beyond that, the receiver, if it is on the earth, will the receiver here will not see the transmitter. If you put here the same height, but at a larger distance, this larger distance, you will see that straight line here. It cannot reach the receiver. See, if you connect it, it will enter the earth, so it cannot reach the receiver. So the maximum distance between transmitter and receiver, where there is a line of sight between transmitter and receiver, is this. It will be dt1 here plus dt2. dt1 is twice ae h1 under square root, and dt2 is twice ae h2 under square root. As you can see, this is dm. We call it dm. Now this page is very important also. These things are very easy. You just can copy it and take it in the exam. This because we have in every range, in every zone, we have different equations. So when you solve a problem, how can you know which equation should I use? This page here gives you a summary of all, even a summary for the upcoming lectures, upcoming material. Now, if the distance d max here, d, is between 0 and d max is given by this. 5 degrees is constant, h2 receiver height, h1 transmitter height. If the distance, في حد اجى كأنه؟ شوف مين participants. في معتصم اجى ولا لسه ما اجى؟ كأنه ما اجى، صح؟
لا، موجود.
موجود معتصم؟ معتصم انت موجود؟
لا، عم يحكي على الجروب شات.
يعني موجود بس مش معنا يعني. صح؟
لا، مش فاتح المايك.
طيب مش معنا، شو نعمل عاد احنا بنعمل اللي علينا. المهم بتحسبي or you calculate d max from this equation, okay? And you see if your distance is less than d max, you use the free space equation. Free space, no earth. No earth at all. Now, if the distance, if you calculate the distance is greater than d max here and less than 0.3 dm, dm you calculate it from here. This dm. Here dm. This is dm. If the distance is within this range, okay, we use the flat earth equation, which is twice sine k naught h1 h2 over d under absolute value. Now, we have studied until that, but this is for the future lecture.
بس
نعم.
هلا لما حضرتك قلت بالفري سبيس يعني بنستعمل الباث جين
فرايز.
فاكتور تبع 1 الفرايز اللي احنا
فرايز
تعلمناه.
فورمولا بتعرفيها؟ فرايز فورمولا.
فرايز فورمولا
بي received equal بي transmitted times gain 1 times gain 2 times lambda over 4 pi r all squared. مش هيك بتكون عندنا؟ times 1 minus gamma transmitter squared times 1 minus gamma fries, as if there is no earth. It is purely free space.
Okay.
Do you understand why?
Yeah.
I have explained that in the video, by the way. Okay. Now, if the distance is between 0.3 dm and 0.75 dm, we use curved earth interference zone. We did not we did not reach this stage, but I have put all the. We will come into this formula. We did not give this formula for this 3, 4, 5. We reached only until here. But for the future, you use this page for the whole material of the course, not only for the this lecture. If the distance is between 0.75 dm and 1.25 dm, we use tangent ray zone. If d is greater than 1.25, we use diffraction zone. Now, those are examples. I do not know if you have any question about this example, because it is we already gave an example, similar example, but here we different distances and to find maximum, to find minimum. And we obtain the same answer, 10, 30, 50, 70. We already explained that. You have a question?
I have a question. When we talked about the refractive index, when we refractive index إنه لكل atmospheric level في لها n معينة square root of epsilon r. هلا we don't مثلا when calculating ال P received وهاي الشغلات وال path gain factor, we don't take into consideration هاي الشغلات, right?
No, because we said we put instead of the radius of the earth, the actual radius, we put the equivalent radius. Once you put equivalent radius, you use straight rays. No refractive index, no epsilon. We do not use epsilon r. Once we use the actual radius of the earth is equal, r earth is equal 6,378 kilometer. Yes?
Yes.
If you use this radius, the ray will not propagate in straight lines. It will propagate in a curved line. Okay? If you use AE effective earth radius, it is 8,497 kilometers no need to take into account refraction index. The ray will propagate in a straight line. Okay, so you do not use epsilon r or no. Just you put. I told you that this material, this course is an easy course. It's not difficult. It is an applied course. You use it directly in the field of engineering. So it does not have complicated equations. The equations are simple, just to understand how to apply it and to make design. So once you use the effective earth radius, you use straight rays and you do not use epsilon r, no refractive index, nothing.
Okay. Dr. Bas, another question regarding the same thing, the effective earth radius. If it's possible, يعني هل بإمكانك مثلا تحكي لنا يعني how did they come up with the effective earth radius?
Yes, I explained that in the video. It seems that you did not see the video, yes?
I did see the videos, but maybe I did not like catch.
Okay, no problem. Yes, I will choose an empty area here to draw in. This is the earth, okay?
Yes.
And this is the ray is supposed to move in this direction, yes? In this here, like this.
Yeah.
Okay, if this is transmitter, here, and this is the receiver is here. Okay. I will put it like a tower so that you will distinguish between the lines. So this is if the air density is uniform with height. If it is uniform, this means that the ray will propagate in straight lines. Now, since the air density decreases with altitude, this means that the wave will propagate in this. It will go like this, maybe, yes. It's difficult to draw now because we need very accurate drawing. It will, here, the angle, maybe it will go like this. It will not reach the receiver. You see, it will not reach the receiver. Here. Okay. It may propagate like this. It is curved. Now, to make this straight line, yeah, sorry for this drawing like this. Now, assume that you have grabbed the earth here. You have a good big hands and very strong hands here. Okay. You grab the earth from here. Okay. And from here. Okay. And you have increased the radius. You have stretched the earth to increase its radius. Okay. So the earth has a larger radius. Like this, for example. I don't know. Yes. Okay. I can draw this like this. To be tangent like this. Okay. Now, if this also ray moves with the earth when you stretch it, okay, this will be a straight line in this case. This line here will become a straight line. Because this is a circle also. This is a circle with large radius. When you increase the radius of this and the radius of this, the circle with increased radius will become a straight line. So this means that to obtain a straight propagation, we need to increase the radius of the earth. They calculated the increase. It was a factor of 4/3. So we have to multiply the actual radius by 4/3, okay, to obtain the effective earth radius. I do not know if it is clear now.
Yeah, it's clear.
Okay. Okay, another problem. Just problems, only problems on the topic. We have different problems. This problem, I think, maybe, I do not know, did you see the video on this problem?
Yeah.
Because this problem is not easy, by the way. It combines the free space propagation with the earth propagation, with the Fry's formula. It is not easy. However, if you concentrate, you understand it. You have any question on this problem? Other problems are the same, but this has a different idea.
Yeah. إذا في مجال نروح عند ال path gain factor.
Not for this problem. You do not want this problem.
Yeah, not this problem. The one before.
Okay. Definition, you mean definition of the path gain factor?
No. ما مش definition. I mean نفس example.
نفس example. Okay, let me go down here. نفس example.
Yes.
Now, if you want, you can forget about this. This is forget about it. We do not need it. And forget about this. And also, you see, forget about this. F is equal to this. And forget if you want about this. Just apply 2 pi over lambda naught, H1, H2 over D. This is an equivalent. Another solution, this is equivalent solution, the same solution, yeah, but with different form. So solve using this equation. Solve it, you will obtain the same answer. You will find that F is equal a quarter, 0.25. Now we know that F over D is equal 1 over RF. If you multiply by D, it will be F equal D over RF. You understand?
Yeah.
Yes, okay. Now the distance is given here from the question. That distance is equal 8.1 mile. It is called dt. This is given from the problem. So we put here dt, okay, and RF is unknown. You see here, RF is unknown. It's a reversed problem. Usually, RF is known, and you want to find distance. Here, the reverse. That's why students normally they get confused with this question.
Yeah.
Here, the opposite. Normally, we give RF and we require the students or request the student to find the height or the distance. Now it's the opposite. You can see the height is given, the distance is given. So we want the free space range. Now the only unknown in this question is RF. dt is known. So we found that RF is equal 4 dt. dt is given in the question.
Yeah.
So once we know RF, we can use the Fry's formula, no ground. We can use this. You can see this is the power density in watt per meter squared. Okay, you know this?
Yeah.
And this is the power density from Fry's is this. You divide the power by the area of a sphere with radius of how much is 4 dt, because RF is 4 dt now. And you multiply by it again. So this is equal to this, and from this you can find the electric field.
سر هنا we assume إنه ما في عنا losses، ما في عنا losses عند الترانسميتر، ما في عنا losses during during transmission, right?
Which you are speaking about plain earth or about the free space?
لا free space هون عند
free space no losses.
Yeah.
The loss
Yeah.
is no, there are
There's no.
لا في free space losses.
Yeah, I know.
But
the
here we
equation
no, we do not try to be received. This is power density, not be received. Now this is power density. If you want power received, you multiply by the effective area, which is lambda over 4 pi r over 4 pi times gain of the receiver. Yes?
Yes.
And now lambda over 4 pi, and this is 1 over r squared, and here this will be lambda over 4 pi r all squared. This is the free space loss. So this is power density.
Yeah, okay.
The Poynting vector, you have studied that in 307. Poynting vector is electric field squared over Z naught if E is peak value. If it is RMS, no 1/2. And the power density, if you go back to when we gave the lecture on the actual lecture in the university, on the Fry's formula, we have detailed the derivation.
Yeah.
If you go to details, this will give you this. P transmitter, it will be distributed over a sphere of radius RF, which is 4 dt. You divide the power by the sphere, you will get the power density. But this, if the gain is isotropic, the gain is 1. If the gain is G, you multiply by the gain of the transmitter here. Okay? And from this equation here, everything is known except the electric field. You find the electric field. That's the whole story. Now I think we have to stop because now it's 10:30. No, I think we have, it is 40 minutes. We have 10 minutes if you want. We can start the next chapter if you want. You have any question about this chapter? No?
Yes.
No, after we have diffraction. The next chapter is diffraction. This chapter, I will go back to here. Diffraction and scattering. We have this common, situation, scenario. We have a mountain here, or a building, or any obstacle, a tower, anything, which obstructs the transmission from transmitter to receiver. Here, partial obstruction. So you can see there is direct ray, and there here diffracted ray from the tip of the mountain. This is called the clearance. Now, this is called mid-path obstacle. Mid-path does not mean that it should be in the middle exactly between. It's in between. Mid means in between here. So this is the schematic of this situation. We have, this is the obstacle height is h, and here the transmitter height is h1, the receiver height is h2, and this is the direct ray. And this is the clearance. We want to find the minimum clearance for good transmission. This is design problem. D1 is distance between transmitter and the obstacle, and D2 is the remaining distance, and D, of course, is D1 plus D2. Now, no need to go through this derivation here. Here, electromagnetics, it is difficult derivation. No need to go through it. Just we need this equation now. We need simple equations. We need this equation. Okay, this equation is important. We need it here. I will derive it now. Or I will decrease the. I will make zoom to see both figures on the same, because I want to explain. You can see. I will increase a little bit. Okay. Like this. This is okay. That's okay. You see now? Is it clear for you?
Yeah, it is.
Yes, okay. I want to calculate at C. Okay. No, normally theta C is almost zero, small. So this distance is equal to this distance. This is very, very small. It's almost zero. We can say it. I have written here. Cosine theta C is 1. Theta C is 0. Okay. Now, if we draw this line here, okay, straight line. Now, this distance squared, this here, this distance from here to here. This is this distance. You can see this distance is equal to, this is H2 minus H1 is this. This is H2 minus H1. Yes, this distance is H2 minus H1. Yes?
Yes.
And this is proportional to this. This distance is equal H2 minus H1 times the total D over D1. Times D1 over D, sorry. Times D1 over D, yes?
Yes.
From similarity of triangles. So we said H2 minus H1 divided by D is equal this distance over D1. Here, H2. I will write it. H2. Oh, sorry. I think that I have the option also to write here. Let me try to write here. Let me write. Sometimes it writes, sometimes no. That okay. Let's go back to the pen, and I do not want to lose the time. Okay, we said H2 minus H1. This is H2 and this H1. So this is H2 minus H1 over this triangle is similar to this triangle, yes? So this is H2 minus H1 over total distance D equal this unknown distance. Let's call it, for example, H, for example, H3. Let's call it H3. H3.
Okay.
Sorry for the. This is H3 over D1. Yes, exactly. So H3 is equal H2 minus H1 times D1 over D. Here it is. H2 minus H1 D1 over D. This is H3. Okay. But here the clearance is H3 plus this distance. This distance here. This is here, from here to here is H1 minus H. Here it is H1 minus H. And theta C is 0. That's the equation. Okay. Clear?
Yeah.
Okay. Now I will increase the, make zoom to see. Okay. Now you can't forget about this. You can just go through this, but we do not need it anyway in our solutions. We need only, I will go back to this figure, but we need, this is 2D Fourier transform. We do not know this, I think. You did not study this. This is 2D Fourier transform and antennas. So it is beyond the scope of this course. We need this equation only. We need this equation. This is E with obstacle over E with the free space is equal FD. This is the path gain factor also. The effect of the obstacle. But here, since we do not consider reflection from the tip of the mountain, if you remove the obstacle, the problem will be free space, not the ground. You understand this? I will just explain. Here, logically, if you remove the mountain, okay, the problem becomes plain earth propagation, yes?
Yes.
But because we did not consider reflection from this point, from here, any reflection is obstructed. It's not taken account. It's not taken into the equations. It's not considered in the equations. So if you remove the mountain, the problem becomes only free space. You remove all of this. You remove the mountain and the earth. If you remove, you do not remove the mountain alone. So the problem is either obstacle or free space. That's why we compare with the free space. We do not compare with plain earth. The comparison is with the free space. So this is called FD. FD is given by this graph. We use this graph because the result is another integral. There is no compact form for the result. We use this graph. This graph in terms of normalized at C, and here 20 log FD, because FD is in terms of electric field, so it's 20 log. And as you can see, when capital HC is greater than 0.8, the attenuation is small. So here it is 0 at 0.8. So usually we choose HC greater than 0.8 to find the clearance. Now capital HC is given by this equation. We need also this equation. You can see the result is another integral, indefinite integral. So it's not difficult to find. We use HC here. HC is given by this equation. We need this, and also we need this. This is the equation. This is the final equation that we know. So capital HC. HC is the clearance, the distance between the tip of the mountain and the ray. This is HC. And D is the total distance, and D1 is distance from the transmitter to the obstacle, and D2 is the main distance, and lambda naught is the wavelength. So this is an example here. So we choose, as we said, we choose HC to be greater or equal to 0.8, so that the mountain will not affect the propagation significantly. An example here, a simple example. Frequency is 1 gigahertz. It is explained in the notes. 1 gigahertz, and D1 is given, D2 is given. You find a small capital HC, and you choose HC to be 0.8, and from that you can find a small HC. So HC turned out here to be 24 meters. So in the video I have put the calculator and calculated everything, you know, online. So this, I think we do not have time to study this. This is because now it's 10:40. This is the rain here, rain cell, and we have target inside the rain cell. There is an airplane. Okay. No one with us? No one of the.
I think
في حد موجود؟
معتصم لسه معنا.
معتصم موجود؟ موجود؟
لسه موجود بالشات.
لا مش سامعنا، مش معنا على الخط يعني.
لا مش معنا على الخط.
للأسف. شايف كيف؟ فهي الرين سيل هذه اللي عندنا هنا رين، وهنا فين الرادار، وفي داخله طيارة. So the scattering back towards the radar will be from the airplane and the rain, but because the rain is has much more greater volume as compared to the airplane, the reflection from the rain or the scattering from the rain is much more than that from the airplane. We use the radar equation as it is that we already studied. We use the radar equation. Here you can see the radar equation. Oh, here I think it's here somewhere here. Here. This is the radar equation. PR. This is the radar equation. We know this. This is PR equal lambda naught squared over 4 pi cubed R naught to the power 4 P transmitter, and G squared, the gain squared. This is the only difference. Sigma, instead of sigma we put sigma times V. This is sigma for the rain. This is the sigma density, which is the radar cross section of rain per meter cubed times the volume. V is the volume, not voltage, not anything else. Only this radar equation, the only difference is here. And the volume is given by this equation here. The volume of the rain cell is given by C tau over 2 R naught squared pi theta 1/2 squared. C is speed of light, tau is the pulse duration of the radar, and R naught distance between the radar and the rain. And theta 1/2 is half of the half power beam width. Not half, it is half of the half. You understand? It is half of the half. Here. here. You see, from here to here, this is half power beam, what's called, yes?
Yes.
So this distance, this angle, the half angle is called half of the half power beam. This theta 1.
Yes.
So the equation, and sigma bs is given by, there is sigma bs given here. Here is sigma bs. It's given by this equation. It's meter cubed by meter cubed, meter squared by meter cubed. It is 9.05, 10 to minus 14 over lambda naught is the wavelength to the power 4. This drain rate in millimeter per hour. If it is 10, you put 10, 20, 20 to the power. And you plug this here to obtain the received power. That's all. That's it. We have finished the second chapter because I already explained that in the video, so we just put some notes here. That's all. We have finished the second chapter. I think we have now the time is over, and thank you for listening. If you have any other question, please let me know, and please tell your colleagues to because we will meet on Thursday at 9:30. So everyone should attend, because if there are exams after after we go back to the university, or if there are online exams, this material will be within the exam material. So thank you.
Sir,
Yes.
regarding the project,
Yes.
when are we supposed to submit it?
Submission means that we need to presentation, and we cannot make a presentation until we unless we go back to studying. Yes.
Oh, so we can't have like an online online presentation or something like that.
Just to stop